Okay. So chapter 7 is all about the periodic table, all about the trends on the periodic table, and why they are that way. So a trend means how something changes as we go across, as we go down the periodic table. So this is like easy. Elements in the same group have similar chemical properties. Properties are not identical, however, but they're similar. Okay? And this is pretty easy. Elements in family 1, if you remember, all of their electron configurations would stop with S1. The only thing that would change would be the number in front of it, right? Oops, that's a 3. But they would all essentially have one valence electron. So if they all have one valence electron, they all do chemistry the same way to get rid of that one valence electron. I'm very worried about the sound of my projector. Quinn, if it starts throwing sparks out and your hair lights on fire, I apologize. But you could sue the school probably. Not even have to go to work the rest of your life. All right. So the reason why they have the same chemical properties generally is because they have the same valence electrons. All right. Dmitry Mendeleev and Lothar Mayer independently came up with the same conclusion about how elements should be grouped. No. All right. And so this is just a timeline of when things were known.
At the same time?
Around the same time, probably. So things that were known since ancient times were the things that were colored or valuable or like a liquid, shiny thing. Things that they could distinguish. And then as technology kind of came along, they were able to discover more and more elements. Currently, so the bottom row is 1965 on. They just barely found an element. Well, not found it. That's not true. They finally just created an element that stuck together. So there's even one more square. They could come up with it the same way because if you just look at how the elements reacted chemically, it makes sense. They can put them together, and more than one person would do it the same way. All right. So this slide's not that important, but just know that Mendeleev left blanks. All right. He predicted the existence of unknown elements that were later found, and they fit in just perfect. So it's really a pretty genius idea how the periodic table developed, how it hasn't changed since, what year was that? No, it doesn't say. I think it was in the 1850s. All right. So in this chapter, we're going to study and be able to explain, rationalize, observe trends, whatever. The size of atoms and their ions, their ionization energy, and electron affinity. We will then also, as part of this, add its electronegativity, which I don't ever want to write again. It's a lot of letters. But we will explain why these things are that way. And once we understand electronegativity, or ionization energy, electron affinity is, in my opinion, the least important. We will be able to understand why things do what they do. So in order to understand it, you have to understand this idea of the effective nuclear charge. Now, on this next test I'm about to give you, I don't know, I've never given just a Chapter 7 test. I don't know if there'll be any math, really. There'll be lots of things that you have to answer what the trend is and then why. You can almost always put in one of two things and be right. So remember, when you're stuck, put that it has a higher or lower effective nuclear charge. Because if it's lefter, it's going to have a lower. If it's righter, it's going to have a higher. You can maybe get one right just by guessing that it's either higher or lower, one of those two. And then Another one, when in doubt, you can fall back to electron-electron repulsion, which we'll learn later. That's always a good one. When in doubt, throw that in there, and you're probably going to be right. All right, you okay with that? All right, so effective nuclear charge. In a many electron atom, electrons are both attracted to the nucleus and repelled by other electrons. The nuclear charge that an electron experiences depends on those two factors. Okay, it's a balance between the positive-negative attraction of the nucleus to the electrons and the negative-negative repulsion of the electrons. The effective nuclear charge, or what we call Zeph. And when you write a test answer and you talk about effective nuclear charge, write Zeph. There's no reason to waste your time on a test writing the effective nuclear charge. All right? Is found in this way, where Zeph is equal to Z minus S. This is, I guess, math. I lied, but this is not really chemistry math. It says that Z is equal to the number of protons. So how do we find the number of protons of an atom? Well, Timber pointed at the periodic table. It's the atomic number, right? So if I'm talking zinc, zinc has its element 30. It has 30 protons, right? So Z is the number of protons. S is equal to the number, I probably should put a little hashtag in here, the number of core electrons. Now, the core electrons, I don't know, don't overthink this. The core electrons is the number of electrons in the previous noble gas. So what I mean by previous noble gas is that you go left on the periodic table till you run out, and then you go all the way back to the right, and it's the noble gas above it. So I don't know, if you look, we're talking here about Na. Na's element number 11, go left, and so you're out of room, so you would go up and over, and it would be neon. You all right with that? So the core electrons is always equal to either 2, 10, 18, 36, 54, or 86, because those are the electrons of your noble gases. All right? So Zeph is very easily calculated. If you have sodium, it is element number 11. It's noble gas. Before it is neon, which is element number 10. 11 minus 10 is a 1. Yes? For us, we're going to be just fine going back to the previous noble gas. Every single time we'll be fine with that. You all right with that? Okay. So we would just say this is a 1. A 1 what? 1 that no one cares about, but it's a 1. All right. Then we have chlorine. Chlorine is element number 17, but its previous noble gas is also neon. So its effective nuclear charge is 7. Now, what does 7 mean? We don't care. But you do care that 7 is significantly bigger than 1, right? We just care about these numbers when we're talking about the comparison to something else. All right. So just for practice, not that it's going to be hard, hopefully, but find Zeph for the following 3 elements. That's an S for sulfur, Mg, and Li. And hopefully you'll see a very easy pattern. Maybe pattern's the wrong way to put it, but you'll see an interesting relationship. had this muted for the last couple minutes, but I don't think that I changed anyone's lives, right? All right. So is everyone okay with just that simple idea? That a metal is a loser because it has a small effective nuclear charge. Or in other words, because the nucleus does not hold on to the electron as tightly in a metal as it will a nonmetal. It's all about the effective nuclear charge. All right. So I just have this picture. This is from last year, but it's the same idea. And before really we talk about reactivity, we typically talk about the size of the atom. So we have the size being defined as the distance from the nucleus to the outermost electron. Make sure that you have that. And if you just get it, that's fine. You don't have to write it down. But it's important to know what I'm talking about when I say size. All right? So the reason I take a moment and pause and make sure that we hammer this in is because a lot of times kids think size just means it's mass. And mass in this definition has nothing to do with what we're talking about. It's how far away the electron is from its nucleus. And we say the electron, we're talking essentially about the outermost. And in chemistry, we have a name for what we call the outermost, the valence electrons. Okay? So this idea of Zeph, I just used it to explain why metals are losers, right? And now we can use the idea of Zeph to explain why metals are so much larger in size than nonmetals. And that is for this reason. The red things, I'm sure when I drew this, were representing rubber bands. So I don't care what this element is, but I know it's in family 1 because I just wrote 1. Well, that's stupid. Just trust me. It's in element 1. I thought I was cool, but I'm not. All right? So it's in element 1, or in family 1. It has a Zeph of 1, or it has 1 rubber band, essentially. All right? Then, so this would be a metal. Then we come over here, and I don't know, probably 7. This would be my nonmetal. And now that I have 7 rubber bands, or the attraction is 7 times greater between the nucleus and the electrons, the electron is held much closer. We okay with that? So the size of the atom is indirectly proportional to the effective nuclear charge. Now, you've taken enough tests that you know I like fill in the blanks with the word directly and indirectly related. So what did I just say? The size, oh boy, of the atom is proportional to its effective nuclear charge. What was the word I put here? That's okay, because remember, a large effective nuclear charge means a large pull on the outer electrons, which means they reside closer. So it's an indirect relationship because a big number will result in a small size. You okay with that? All right. Now, on the test, it will say, like usually I have 1 free response, math, for chapter 6, and 1 free response for chapter 7. And chapter 7 is like 10 statements that are all true, and you explain them, if I remember right. So one of the statements will say, um, like family 7 or nonmetals are generally smaller than metals. And you have to tell me why. So why don't you write an easy explanation to that question, put it in a box, and then write in your notes, this is on my test. So the rationale says, I don't know exactly, nonmetals are generally smaller than metals. Why? Oops, I got ahead of myself. So put your best explanation right here. Box it, highlight it, whatever you need to do, and tell yourself, hey, this is on my exam. Oh. I got it this time. All right. Show your lab partner your answer. Make sure you agree with each other. That's perfect. Turn this off for a minute. See what happens when I turn it back on. What? When they design the school, think about this, all of you that want to be structural engineers or whatever. Do you see anything wrong with where my projector is mounted? What? Okay. That's not my complaint. It's okay though. The wires, whatever, they should come out that hole. There's a hole design, but it's way too small. But what, Logan? The heater. That thing's blowing very hot air into a machine that makes a lot of heat and is designed to blow heat out. So it sucks hot air in and it tries to blow even hotter air out. So, um, what's that? I've done that before. They've taken it out because it looks ugly. I don't know, it didn't help. I have a projector behind here that eventually died because it overheated, and I have a projector at Little Mountain Dome that overheated. But, okay, we'll turn that back on in a minute. on these. And of course, even though you told me, I forgot to unmute him. All right? So for video watchers, because nonmetals have high effective nuclear charges, which pull their electrons closer to their nuclei. Yeah. Oh, you stretch that. It's all right. All right, let's turn this on and hopefully it won't blow up. It's right. In like 20 minutes, this room will meet the temperature on that thermostat, and then the rest of the day it'll actually be cold. It's the weirdest room that there is, because the fresh air that they bring in, once that clicks, the fresh air that they rotate through here is cold because the intake is straight from the outside. All right. So there's some tutorial videos that I have on there. In your notes, a lot of times, that didn't help at all. Oh, well. When I do this, it might be helpful for you to draw a simple periodic table, put an arrow that explains or shows the trend, and you might underneath it want to write your explanation. That's up to you, but that's a pretty good thing. I never labeled this, I guess. This would be for Zeph. Or no, sorry, this is size. If I put an arrow for Zeph, it would be the exact opposite way, right? Because size and Zeph are indirectly proportional. All right, easy enough, hopefully. Already said that, All right, I didn't say this, so let's make sure we point this out. These screening electrons, double check that yep, I'm on. We subtract them because of this idea, and put this in your notes. Valence electrons do not shield the nucleus as effectively as core electrons. So there's a good maybe 2-3 paragraph explanation of this in your textbook that I'm sure all of you excitingly read this weekend. But when you have a shell that we consider completed, then we have what we call a core of electrons. That shell, it's full of electrons that are repelling each other, right? But they're also repelling electrons that you add to it in what we would call the valence shell. The valence shell, since it's not complete, is not as organized and does not push electrons away as strongly as a core electron would. Now that was 30 seconds of I don't know, but hopefully it sort of made sense. Because remember, it's a battle. If we are a valence electron, it's the battle of how hard you're being pulled in and then how hard other electrons are pushing you out. Go ahead.
Stopping that innermost shell from being attracted into the
And collapsing. Well, depending on what you believe in, that might be a question you have to ask your maker. That is a very, very good question. The idea is that they are moving with enough energy, kind of like our planet around the sun, that they will not lose energy and spiral into the nucleus. But why? No one knows. Because if you think about it, all matter, every electron and every nucleus should eventually come together. And then matter as we know it would cease to exist. But this quantum energy keeps it out. Very good question. All right, you kind of all right with screening? Core electrons screen better than valence electrons. All right, so this is the overall summary. The bonding atomic radius tends to decrease from left to right across a row due to increasing Zeph. Now, I spent 20 minutes talking about the side to side. The up and down, I'm going to spend 30 seconds on. That was a stupid box. It increases from top to bottom of a column due to the increasing value of n. And to me, that's a stupid way of explaining it. But if you remember, as we went down, we had like 1s2, 2s2, 2p6, 3s2, n, that this is referring to, n is talking about this number. As we go lower on the periodic table, we add more shells, and shells take room. Okay? So its size increases the lower you go because you've added more shells. And then that awesome term I told you could get away with, you have more electrons repelling electrons. Electron-electron repulsion. But mostly, as we go down, they are bigger because we are increasing the number of shells that we're filling. Okay? So those are your two examples. Both of them are tested. One we already wrote, didn't we? And then the other one, maybe you want to write it now. No. Zeph for lithium is what value? It's 1. Zeph for sodium is 1. Zeph for potassium is 1. Okay? So up and down has nothing to do with effective nuclear charge. It's all about having a greater value of its principal quantum number or adding more layers or shells. We good with that? Okay. Remember 5 minutes ago I said in 20 minutes it's going to be warm enough and it's going to start bringing in cool air? We're already there. So in an hour this room will be cold. It's amazing. But they installed a switch over the break, and Mr. Burt came in this morning and pointed out that it doesn't do anything. Yeah, well, I don't want to accept that explanation. All right. So far, two things that'll be tested. Size is smaller as you go right or bigger as you go left. And size is bigger as you go down. You have to be able to explain both. Go ahead.
That's the biggest element we know?
Right here. Well, there's a reason it's not listed, but it would be like right here. It would be bigger, yeah. The reason it's not listed is it's radioactive. So they typically don't put things that are radioactive on charts like this because that means that their nucleus is falling apart. But yes, it would be. So when asked, I tell kids, just remember the two F's, F and FR. Those are both your biggest and your smallest besides family, or the top row. Now, F and FR are also going to be your most reactive. And they're the most reactive because they are so small and so big. I went to Disneyland and lost one of my kids. Remember that? Did I tell you that? My daughter kind of ran away. That was not fun. I went to Disneyland before with 2 kids and we never lost one. The more kids you have, the harder it is to see your kids, right? All right? I only have 4. How many electrons does rubidium have? 37, right? That's a lot to keep track of. And go lower, cesium 55, francium 87. It's a really, really big atom with a lot of electrons to account for that are very far away, right? So it's very easy to remove an electron because the electron's not close to the nucleus. The farther away it is, the more there is, the easiest it is to plug. All right? But then you look at F. F does not have very many electrons, and they're held extremely close to the nucleus. So you can't remove an electron from F very easily. But since it's so small, its nucleus, its effective nuclear charge, can overcome the effective nuclear charge of FR. And if they get by each other, FR loses one easy, and F does what? It takes it. And it would do it very aggressively, very exothermic. If you put F and FR together, it would be explosive. Like,
Does it like when new electrons added to an atom, it takes in when does it releases?
well, it's going to be a balance. So adding, and we'll talk about this, this is really tricky. Adding electron to something always requires energy. But something like F and FR or any ionic compound is exothermic overall because of what we call the lattice energy. And that's the energy when all these free things are moving around doing whatever they want and then they are stuck. And it's like two things running into each other that produce a lot of heat. So it's the balance between those two forces. All right. So here was another picture. Down and left is big, up and right is small. You got Zeph for side to side and more shells for up and down. Now, ions, everything just seems to blow up all of a sudden. Ion size will depend on effective nuclear charge. It will depend on the number of electrons, and it depends on the orbitals in which electrons reside. All right, on the test, I know that I ask you to explain calcium. And it will say that the calcium ion is smaller than the calcium atom. And it will say why. Okay, so we're looking at this part of the picture right here. So once again, it says the calcium ion, Ca plus 2, is smaller than the calcium atom. Oh, I did so well on the pink. Yeah, that's pretty good for me. And then we'll ask why. And your temptation would be to say something about Zeph. Because Zeph, I told you, you can almost always get away with Zeph. But Zeph has nothing to do with it this time. Because it's still calcium, sort of, right? But what you have to understand is the chemistry. We say metals lose, right? Nonmetals gain. We've said that all along. So let's make sure we understand what we are saying when we say a metal loses. If calcium becomes Ca plus 2, that means it lost 2 electrons. That also means, look, calcium is in row 4, right? Its electron configuration would end 3p6-4s2, right? Right. So if it loses 2, this is gone, right? It loses the 4th shell completely. And it's like we've now moved up. And if you remember when we went down, they got bigger because we added shells. So if we're going up, we must be getting smaller. So one more time, the calcium ion is smaller than the calcium atom because it lost its outermost shell. That's what metals do in an electron, like simple metals right now. They abandon their outermost electron shell. If we reduce the principal quantum number, then we have an ion now that's small. All right? Then I believe the one on the test for nonmetals is fluorine. And it will say that the fluoride ion is larger than the fluorine atom. And it will ask you why. And this is the one where you can throw in and just be fine. By gaining an electron, we didn't gain a shell, right? We don't gain a shell. We complete the shell that they already had. But Anytime you take an electron and you put another electron by it, what do they do to each other? They repel. The more they repel in a like 3D sphere, the larger the sphere has to be. You okay with that? So the fluoride ion is bigger than the fluorine atom because the ion has greater electron-electron repulsion. In order to get that 5 out of 5, you have to have the term electron-electron repulsion. These are usually pretty easy, and it's a great test to start off your second trimester. It's usually paired with chapter 6, so I don't know. It should be something that, I mean, no one looks forward to a test, but everyone looks forward to starting off with the easy test. There are some very hard ones this try, so don't think, oh, everything hard is behind me. We are starting into a fairly, well, it depends on your definition of easy, but my definition of easy, we're starting 3 or 4 easy chapters now. And we'll end this try with 1 or 2 pretty dang hard ones. And then we start next try, and all we do is very hard ones next try. But there's only a couple left next try. Are we okay with sizes of ions versus atoms? You have to be able to explain both. All right. Here are a couple of questions. Well, I guess last year I got farther. Try these 3, and then we'll see if we have any time before the bell rings.